All right, we're continuing our theme here of a day with Newton, Euler at Dollywood. We are considering 3 examples: the lemon twist, the dizzy disc, and the timber tower. This example will work the dizzy disc. And if you go to the YouTube link, you can see somebody that recorded being at Dollywood and the dizzy disc. The dizzy disc has this big track. We'll assume it's a circular track. There's a sled on the track, and on that sled there's this rotating disc. Now, it looks like there are wheels under this disc that are causing it to spin at some known rate. For our purposes, let's assume that that's free, that the wheels are driving the cart up and down the track, but this rotation here that you see is free. Our curiosity is, what's the motion of a rider on the dizzy disc, given some motion along the tray, and let's write Newton-Euler equations to describe that, as well as the constraints needed to define the motion. So we go over here to the dizzy disc, go over here to our notes and start drawing out. So when I saw the dizzy disc, I saw this tray. I don't know if you call it tray, a big cart. And I'm interested in me, or us. Here we are, sitting on a chair. I guess they're kind of straddling on a chair, aren't you, on the dizzy disc? You're located about some axis here by some, we'll call it a distance r. And underneath, not really shown very well in my picture, there's the wheels, and the wheels are running on a big track. Goes down and up, both sides, and that supports off to the ground. And you're rotating back and forth. Okay. So for our model, let's, so how are we going to treat that? Well, we said that this was a constant radius track. So based on that, let's make the assumption that I can work my way back up to the center of rotation of the track right here. And the track's radius is r. And my cart is moving along the track with some motion, and that motion, we'll say it's going to be given by some alpha and some alpha dot. Then down here, the cart's, in this case, we're assuming free to spin, and we'll assume it's free to spin by some theta. By the way, in this case, my alpha is about this axis. Here I'm free to spin about some theta, and I've got a little r here. Start the problem off, I'm going to assume I have some inertial frame. I'll define it here. Say it's an N1, N2, N3. I'm now rotating first. Oops. First, I'll attach a frame to this cart, rotated relative to the end frame by some alpha. When I do that, let me go back and try these frames again. Okay, I'll tell you what, to make this, to help make sure this is clear, I'm going to erase just a few things. So I'm going to move my rider over. Oops. Here's my cart. Put my rider over here. That's the center of mass. That's the center of mass of this great big cart. Not very realistic, but that's the way it goes in our problem. And then we've got our main frame here. So let's say that's just coming, we'll just call that guy coming out of the board. Or I guess I'm going to try to make everything be 3D somewhat. That is my N1 axis, yes. That's my N1, N2, and N3. And I'm rotating around the N1 axis by the alpha beta. So I first get a rotation around the N1 axis, and that will put my new frame, and that's the one I was going to draw with red. My new frame is down here. So that's my, I'll call it my intermediate frame A. So that'll be my A3. This will be my N3. Oh, my A2. And then this will be my A1, which is still the same direction as my N1. Then I'm going to rotate around the A3 by some theta to get a body fixed frame located up here. It's going to give me some B2. So the rotation from A2 to B2 is my theta. And this is a rotation around the 3, so the 3 is preserved, same direction for 3. A B3, and then finally some B1 frame. All right, the relationship between these frames are given as first a projection of A onto N as a rotation around the 1 axis by alpha. Followed by a rotation around the 3 axis to project us from B back to A. That rotation is, rotation around the 3 by theta, so it's a C theta, negative S theta 0, S theta, C theta 0, 0, 0, 1. And we may need the composite rotation, so the projection from B to N is the multiplication of the 2, so it gives us C theta, negative S theta 0, C alpha S theta, C alpha C theta, negative S alpha, S alpha S theta, S alpha C theta, C alpha. And okay, and let's next move. So okay, to do Newton-Euler equations, we need the angular velocity and acceleration of the body fixed frame relative to the end frame. And we're going to need the velocity. Frankly, we need the acceleration of the center of mass. We'll call that G for this guy. So let's first derive those. We'll start with the angular velocity. Angular velocity of B to N is the sum of those two. We first have an alpha dot around the A1 plus a theta dot around the A3, which is also the B3. That's our angular velocity of A with respect to N, in case you wondered. The angular acceleration, let's rewrite this all in the B frame. To write on the B frame, I need to pre-multiply this guy that's in the A frame by the projection from B to A transpose. So I'm going to pre-multiply by the transpose of this guy. That will give me C theta alpha dot in the B1. It's going to give me negative S theta alpha dot in the B2 and 0 in the B3. And I add it to this guy. So I have my theta dot B3. So that gives me the projection of B to N described in the B frame. I'll now take the derivative of that, alpha B to N. First I take the derivative in the B frame plus the angular velocity of B with respect to N cross with angular velocity of B with respect to N. Of course that goes to 0. When I take its derivative, I get a cos theta alpha double dot minus sine theta dot alpha dot. The second term is going to be minus sine theta alpha double dot minus cos theta dot alpha dot. And then finally theta double dot. If I assume that the angular velocity is constant, which I will for this case, we'll let alpha dot be constant. Of course, you could see when the thing's going back and forth, it's not constant, it's sinusoidal. We could just assume it's sinusoidal. If we do that, we carry it along. I guess to simplify my job, I'm going to assume it's constant, but you could assume it's sinusoidal. If it's sinusoidal, then given some alpha dot, you just find alpha double dot is the derivative of that term. It's going to give you derivatives of sine, so you can go on with that. Next, we need the velocity of g, which is the derivative of r, of vector r going out to g. So going from ground out to g. So first we have a cap r in the negative a3 direction. And then we have a little r in the positive b2 direction. Take the ddt of that. First, you can take derivatives in their local frames. Those things are constant, so that'll be 0. Then I have to take the angular velocity of a with respect to n crossed with this first term. So the angular velocity of a with respect to n is alpha dot 0, 0 crossed with 0, 0, negative r. It's on the a, plus the angular velocity of b with respect to n, which we said was c theta alpha dot minus s theta alpha dot theta dot crossed with 0, r, 0. So we get the first term gives us a k times, an I times a k gives me a negative j, so I get plus r alpha dot. Don't forget that's in the a direction. And here I get an I across a j, gives me a k, so I get a cos theta alpha dot r. A j across a j is 0. A k across a j is a negative I, so negative theta dot r. Get any term there. To pre-multiply this guy by the projection from a onto b, I have b onto a. Here I need the transpose of that. So it's cos. I'm going to multiply by the second column. So it's going to be sine theta, cos theta 0. So it's going to be sine theta r alpha dot, cos theta r alpha dot 0 plus this thing. So it's going to be minus theta dot r 0 and cos theta alpha dot r. Okay, did a couple steps there pretty quickly. That's all in the B frame. One was I pre-multiplied this by the projection from B to A transpose, and then I added that term in. This was in the B frame. Now I'm going to take my derivative, my derivative of A with respect to G. First I'm going to take the derivative in the B frame, then cross with the angular velocity. Let's take the derivative first in the B frame. So that gives me cos theta, theta dot alpha dot r minus plus the derivative of these two, but those are constant. So I get minus theta double dot r. Second term minus sine theta theta dot alpha dot r. That's it. Third term minus sine theta theta dot alpha dot little r. And I have to add in the angular velocity of b with respect to n. Just c theta alpha dot minus c minus s theta alpha dot theta dot. Yep. Cross with this thing, s theta r alpha dot minus theta dot r, c theta r cap r alpha dot, and c theta alpha dot little r. I'm going to do that cross product. I get three terms. I get a I is a j cross k. So again, minus sine theta alpha dot squared cos theta r minus cos theta r alpha dot theta dot. Second term, y is theta dot alpha dot sine theta r minus theta dot squared little r minus cos squared theta alpha dot squared little r. And then finally, the third term is cos squared theta alpha dot squared capital R minus a minus plus sine squared theta capital R alpha dot squared. Those are going to combine. Plus or minus sine theta alpha dot theta dot little r. And I add it to this. So when I put it all together, I get this term is going to cancel with this term. I get a minus sine theta alpha dot squared cosine theta little r minus theta double dot little r. Second term, get a minus sine theta dot alpha dot same thing I have right here, so I cancel that. I get a minus theta dot squared little r minus cosine squared theta alpha dot squared little r. Third term, get a minus sine alpha dot theta. That's funny that those don't. I think I've messed up a sign on one of these. I really expect those to cancel. Well, I really expect those to cancel, although not seeing it, I'm going to leave it there. So these things combine, so I get alpha dot squared capital R minus 2 sine theta alpha dot theta dot little r. I would definitely recommend checking that work and seeing if we can find that term, see if that term cancels out. Okay, so on the Dizzy disk, this is my acceleration. Now I'm ready to write my equations of motion. Let's go back and review our free body diagram. So I had the big tray. My center of mass was up here at me. There is this, this tray is spinning on a revolute joint. The revolute joint here has 5 constraints and 1 freedom. So I got a F in the B1, or I think that was the B2, an F in the B3, an F in the B1. I get a moment around the B1, moment around the B2, and then no moment around the B3. I get a mass times gravity term. That's in the inertial frame. Need to pre-multiply mass times gravity from the inertial frame back to the base frame. The mg is in the 3, is in the -3. So I've got to multiply by this thing. So it's sine alpha, sine theta. I've got to pre-multiply by this guy, but the transpose. I'm currently in the n frame, I want to go to the b frame, so I'm going to multiply by the transpose. It's going to be sine alpha, sine theta. It's going to be sine alpha, sine theta, sine alpha, cos theta. This mg is mg sine alpha, sine theta, sine alpha, cos theta, and cos alpha, and it's negative in the B direction. So now we're ready to start writing those. So some force into B1, I get FB1 minus mg sine alpha sine theta equals mass times acceleration. So mass times negative sine theta alpha dot squared cos theta r minus theta double dot little r. Second term, FB2 minus mg sine alpha cos theta equals mass times negative theta dot squared little r minus cosine squared theta alpha dot squared little r. Third term, FB3 minus mg cos alpha equals mass times alpha dot squared kappa r minus 2 sine theta alpha dot theta dot little r. Sum of moments, get MB1 minus, I need the moment about the centroid. There's going to be a moment about the one direction. Looks like I'm going to get a negative RFB3 equals I1 alpha 1. What's our alpha? Our alpha was negative sine theta, theta dot alpha dot. Yeah. And since I'm going to write the other one down, negative cosine alpha, theta dot alpha dot, minus I1 minus I3, or excuse me, I2 minus I3 times omega 2 times omega 3. So I need omega 2 and omega 3. So it's sine theta alpha dot theta dot. Interesting. Same term. Just get the product of those. Second guy, MB2, and I don't have any other forces causing moment about B2. Oh, no, I forgot the moment. So it's got to be FB3 minus mg c alpha. This equals I2 minus I3 minus I1. I3, omega 3 times omega 1. Let's check those out. Omega 3 theta dot, omega 1 cos theta alpha dot. So it's cos theta alpha dot theta dot. And then finally, MB3, the moment around 3 is going to be a plus RFB1 minus mg sine alpha sine theta equals I3 times my alpha 3, which is theta double dot, minus I1 minus I2 times omega 1 times omega 2. So I get sine theta, cos theta, alpha dot squared, negative. All right, there's my three equations. In this problem, I had 5 constraints. 1 degree of freedom, which is my theta double dot. So my unknowns are listed that way. We'll highlight them. I'm going to highlight my unknowns. So I had an FB1, FB2, FB3, theta double dot, which shows up there and here. MB1, MB2, oops, no MB3, get carried away. Here's the FB1 and FB3 again, and there's my theta double dot. So I will cast these in matrix form. I have some constraint, so I'll try to leave it up here. Times a set of unknowns, FB1, FB2, FB3, MB1, MB2, theta double dot, and I start writing my equations. So the first one is a 1 times an FB1 0 times the other two forces, 0 times the two moments, and a positive m times r equals everything else. And I moved it to the other side, so it was m times minus sine theta alpha dot squared cos theta r plus g sine alpha sine theta, and so on. I'll do one more. Second row, 1 times FB2, looks like that's all I have, equals mass times negative theta dot squared r minus, and don't forget the g term. So expand that out, and that gives you then equations for all these terms to be considered simultaneously. If we look at the last equation is going to give us an r in times FE1, 0 times FE2 and 3, 0 times those moments. It's going to give us a negative I3, theta 3 double dot, and then over here I'll get a negative I1 minus I2 times the sine. Those negatives are going to cancel, so sine theta cos theta alpha dot squared plus RMG sine alpha sine theta. I can simplify this somewhat. I can see these internal constraints are theta double dot's not internal. Theta double dot's just these first two. So I could drop these internal terms and just get a 2 by 2 to solve. I'd have to work out FB1 and theta double dot together. All right, that completes this example.